Hello everyone, welcome to the week 5 live session. Anyone can confirm is I am audible or not? Okay, uh, so let's start the today's session. So in today's session, I will cover 3 lectures, which is lecture number 13, 14, 12, 13 and 14. That is lecture number 12 is on longitudinal and shear strain. Longitudinal and shear strain. Lecture number 13 is based on local volumetric strain and local infinitesimal strain. And lecture 14 is based on similarity in properties of stress and strain tensor. So these 3 lectures I will cover today. So first of all, I will briefly give the overview of these 3 lectures, and then later on in this session, I will solve some problem based on the concepts which is covered under this lecture. So yeah, let's start the today's session. So in the first lecture, that is lecture number 12, it is basically based on longitudinal and shear strain. So I am not derived the whole formula here. You can go through the lecture. You can go through the lecture if you want to see the detailed derivation. I simply just write the formula here so that it will be useful for you. So to understand when I will apply the formulas in the problem. So first of all, the longitudinal strain is given by, so yeah, longitudinal strain. So longitudinal strain at a point in a prescribed direction is given by epsilon. So if we want to know the longitudinal strain at position x in the direction n, so it is given by half of gradient of displacement gradient plus transpose of displacement gradient. Okay, so half of grad u plus grad u transpose times n, and with dotted with n, where n is the direction where we want to find out the longitudinal strain. So this is the formula for longitudinal strain. Using this formula, we can find out the longitudinal strain in any direction. So just to say example here, if suppose the line element direction suppose is in even direction, Suppose line element direction is along E1, then the component of, then the longitudinal strain is given by epsilon at position x along E1 direction. So basically I write the component of this tensor, that is half of grad u plus grad u transpose. So if we write the component, then it will give us half of del u1 over del x1, del u1 over del x2, del u1 over del x3, similarly del u2 over del x1, del u2 over del x1, del x2, del u2 over del x3, and in the same way del u3 upon del x1, del u3 upon del x2, and del u3 upon del x3 plus transpose of this one, that is del u1 over del x1, del u1 over del x2, del u1 over del x3, and in the same way it is, you can write here. So this is the component of this tensor, half of grad u plus grad u transpose, and when we dotted it with E1 component, E1 vector, so component of E1 is given by 1 0 0 in E1 E2 E3 coordinate system, and it is dotted with component of E1, that is again 1 0 0, and if we calculate this, we found that longitudinal strain along E1 direction is given by del u1 over del x1. So yeah, del u1 over del x1. So longitudinal strain along E1 direction is given by del u1 over del x1. Similarly, longitudinal strain we can find out in similar way. Longitudinal strain along E2 direction, that is del u1, del u2 over del x2, and longitudinal strain along E3 direction is given by del u3 over del x3. In the same way, we can find out this one. So this is about the longitudinal strain along any direction. The next topic that is covered is shear strain. So shear strain. So shear strain is nothing but the change in angle between the two line elements. Okay. So initially the two line elements are perpendicular to each other, but if there is any change in the angle between them, then we say that there is a shear strain between the two line elements. So suppose this is a line element along two direction, these two line elements, and after deformation, this two line element become this one. And earlier the angle between these two elements is 90 degree, but now the angle between them is, suppose this angle is beta. So shear strain is defined as a change in angle between the line elements. So what is the change? That is 90 minus beta. So shear strain is nothing but here 90 minus beta. So this is a change in angle between the two line elements, and this is represented as the shear strain. So there is a formula that is derived for this. If we know the deformation gradient and if we know the displacement gradient, then we can find out the shear strain between these two line elements, between any two line elements aligned in any direction. So suppose we have two line elements which are aligned in along m and n direction. So the shear strain in that case is given by alpha is equal to grad u plus grade u transpose, that is displacement gradient. Grade u is the displacement gradient times m dot n. So this is the shear strain between two line elements. So in this way we can find out the value of the shear strain. And the above formula, that is this formula, depend on the direction of the two line elements, because here you see that we have the direction of two line elements, that is the m and the n. M and n are the unit vector aligned along the two line elements. So it depends on the direction of the two line elements. So suppose at a given point, so we can say from this one that at a given point different pair of, there are several shear strain value occurs at a point, because we have different pair of line elements at a point. So we can have different sets of shear strain corresponding to different pair of line elements. So from this we can infer this one. Next is the in both the case you see that in the case of longitudinal as well as the shear strain, there is a component that is grade u plus grade u transpose. So there is a physical meaning of this one, that is the significance of grade u plus grade u transpose. So this is nothing but, so first of all I write here the significance of half of grade u plus grade u transpose. So if we break out the matrix, that is, suppose if we want to write this tensor, the second order tensor in component form, so the component of this one, that is half of grade u plus grade u transpose in E1, E2, E3 basis can be written as, if we break out the component in component basis, it can be written as del u1 over del x1 half of del u1 over del x2 plus del u2 over del x1. Similarly, half of del u1 over del x3 plus del u3 over del x1. I hope it is visible to you. And the diagonal elements are del u2 over del x2 and del u3 over del x3. Yeah, so this one become half of del u1 over del x2 plus del u2 over del x1, because this one is symmetric. So and the 3 1 is symmetric to this one, so half of del u1 over del x3 plus del u3 over del x1, and this one is half of del u2 over del x3 plus del u3 over del x2, and this one is symmetric to this one, so half of del u2 over del x3 plus del u3 over del x2. So this is the component of half of grade u plus grade u transpose tensor. This is a second order tensor and it has 3 by 3, that is 9 component. So you can see that the diagonal element, that is if we see the diagonal component of this one, so we see that it represents the longitudinal strain along E1, E2, E3 direction. So here I pointed, I write down one note here, that is diagonal elements here represent longitudinal strain longitudinal strain along E1, E2, E3 direction. Okay. And the off diagonal strain, if we see the value of the shear strain, that is grade U plus grade U transpose m dot n, and here it is half. So we can say that the off diagonal element represent half of the shear strain, that is gamma by 2. So shear strain also denoted by gamma. Later on I will use that. So we can say that the off diagonal elements represent half the shear strain. Okay. So these two topics were covered under lecture, that is longitudinal and shear strain. So I have wrote the two important formula here. The first one is the longitudinal strain, that is given by half of grade U plus grade U transpose n dot n, where n is the direction where we have to find out the longitudinal strain. And then I wrote down the formula of shear strain, that is given by grade U plus grade U transpose m dot n, where m and n are the direction of two line elements. And I also told you the significance of half of grade U plus grade U transpose. So if we break out the component, if we write down this tensor in component form, then we see that the diagonal element corresponds to longitudinal strain along E1, E2, and E3 direction, and the off diagonal components represent the half of the value of the shear strain. So this is all about lecture number 12. In the next lecture, which is based on local volumetric strain and local infinitesimal rotation, will be discussed. So here in this section, for volumetric strain is discussed. That is, so I simply wrote down the formula, write down the formula here, that is volumetric strain. So volumetric strain, which is denoted by epsilon V. Okay. So volumetric strain is given by determinant of F, that is the F. I earlier told you in the previous lecture, I told you that this is the deformation gradient tensor, half of determinant of F minus 1. So this is the volumetric strain. And we also know that F is given by identity tensor plus grade U, that is displacement gradient. And if we put this one in this equation, we found that volumetric strain can also be written as 1 plus del U1 del U1 over del X1 plus del U2 over del X2 plus del U3 over del X3 plus higher order terms. And if the strain is small, very small, so this can be neglected, that is the higher order term can be neglected. So it simply gives us volumetric strain is nothing but del U1 over del X1 plus del U2 over del X2 plus del U3 over del X3. So this is the two formula for the volumetric strain. So if we know the value of the deformation, if we know the component of deformation gradient, we can use that formula to find out the volumetric strain. And if we know the value of the displacement, if we know the value of displacement, then we can simply take the derivative with respect to x1, x2, and x3, and then sum over the this three direction, then we get the volumetric strain. So if you compare this one, that is del U1 over del X1, del U2 over del X3, del U3 over del X3, so you can find that this is nothing but the diagonal elements, basically the summation of the diagonal elements. So we can say that it is nothing but the trace of this tensor. One thing I forgot to mention here, that is this term, that is half of grade U plus grade U transpose, we say that it is infinitesimal rotation tensor, infinitesimal strain tensor. It is also referred as infinitesimal strain tensor. Infinitesimal strain tensor, and it is represented by epsilon's second order tensor. Okay, so this is referred to as half of grade u plus grade u transpose. This is nothing but it is called as infinitesimal strain tensor. And if we compare this one, so here we see that the sum of the diagonal element is nothing but the volumetric strain. So there is one more formula based on the infinitesimal strain tensor, that is trace of epsilon. So volumetric strain is also given by trace of infinitesimal strain tensor. Or here you can also see that epsilon tensor is nothing but the infinitesimal strain tensor, and it is given by half of grade u plus grade u transpose. So it is also equal to trace of grade u, because the diagonal element because the diagonal element, if we sum over the half, if we take the component, then grade of u also gives the same component in the diagonal element. So it is also given by trace of grade u. It can also be same as grade of trace of grade u plus grade u transpose. Okay. Trace of half of grade u plus grade u transpose. So it is this one. Epsilon is given by half of grade u plus grade u transpose. So these are these three are the formula for the volumetric strain. Now the next topic is rotation tensor. Okay, so if we write the deformation gradient tensor F, which is given by identity tensor plus displacement gradient, and if we break out the displacement gradient in this way, that is half of grade u plus grade u transpose plus half of grade u minus grade u transpose. So this is the identity tensor, and this is half of grade u plus grade u transpose is epsilon, that is the strain tensor, infinitesimal strain tensor, and this term is the rotation tensor, local rotation tensor. We say this one is the local rotation tensor, and it is represented by W. Okay. So the local rotation tensor, I just simply write the formula here. The local rotation tensor, the component of rotation tensor, that is W. So local component of local rotation tensor in E1, E2 and E3 coordinate system is given by this one, this relation 0 minus half of del u1 over del x2 minus del u2 over del x1 minus half of del u1 over del x3 minus del u3 over del x1 half of del u1 over del x2 minus del u2 over del x1 half of del u1 over del x3 minus del u3 over del x1, and this is the diagonal element r0 here. This component is del u2 over del x3 minus del u3 over del x2, and this one is minus half of del u2 over del x3 minus del u3 over del x3, sorry, del x2. Okay, so yeah, this is the local rotation tensor component. And if we see this if we see this matrix, we can see that it is a nothing but a skew symmetric matrix. So we can form the axial vector from this skew symmetric tensor. So the axial vector W axial vector of W axial vector W is given by, so we write here the component of, that is component of axial vector W is W is equal to, in E1 E2 E3 basis, half of del u3 upon del x2 minus del u2 upon del x3, half of del u1 over del x3 minus del u3 over del x1, half of del u2 over del x1 minus del u1 over del x2, so this is the component of axial vector W. So this is all about the lecture number 13. The next and the last lecture of this session is lecture number 14, which is based on similarity in properties of stress and strain tensor. So I just simply write the similarity here, that is similarity in stress, similarity in properties of stress and strain tensor. So so this side I write the stress property, and here I write the strain property. So in stress we have normal stress of traction, that is given by sigma n dot n, and in analogy of this we can find out the normal strain, which is given by epsilon, that is the infinitesimal strain tensor epsilon n dot n. Next is shear component of traction, which is given by sigma n dot m, and in analogy of this we can find out the shear strain, which is given by gamma mn, which is 2 times the infinitesimal strain tensor n dot m. Okay, here n are the plane normal and m is the direction along which we measure shear. And here n is the direction of line element. And m is the direction of line element which is perpendicular to n in the reference state. So direction of line element perpendicular to n. So this is the similarity between the stress properties of stress and strain tensor. Okay, and we know the stress tensor is symmetric. In the same way, strain tensor, infinitesimal strain tensor, is also symmetric. So we write this here, that is strain tensor epsilon is also symmetric. And we know the principal stress component. Earlier in the previous lectures, I have solved some examples where we have to compute the principal stress and principal stress component. So in the same way, we can calculate the principal strain component with the use of the Mohr circle. And in the earlier one, in the Mohr circle of stress, we see that Mohr circle, we only draw the Mohr circle if there is one condition met, that is the third principal stress lie along the coordinate, one of the coordinate axis. Then only we can find out the other two principal stresses. In the same manner, here we know the, if we know the principal uh, strain along any coordinate axis, along one coordinate axis, if the principal strain is along one coordinate axis, then we can find out the other two principal strain in different coordinate axis using the Mohr circle. So I write here Mohr circle for strain. So in the same way, we have to find out the, first we know the value of the, we have to find out the value of the center. So suppose center is here. If we know the value of the strain component, that is the normal and the shear strain, so we can find out the value of the center, that is epsilon xx epsilon yy upon 2. So this is the center, and along the x-axis we have normal strain and on the y-axis we have shear strain. And we know that the shear strain is nothing but 2 times the value of the infinitesimal strain tensor. So the Mohr circle gives us the value of the half of the shear strain. So if we want to know the exact value of the shear strain, we have to multiply the shear strain value which is computed from the Mohr circle by 2. So we have to multiply the value of the strain with 2 so that we can find out the exact value of the shear strain in the Mohr circle. So yes. So we can say that the maximum shear strain is given by 2 times of radius, because here you see that the radius is gamma by 2, and therefore the maximum shear strain is given by 2 times of radius. And principal strain component is given by epsilon xx plus epsilon yy upon 2 plus minus radius. So this is the formula for to find out the value of the principal strain component. So this can give only two. We will get only two strain, that is epsilon xx and epsilon yy, and we know the value of epsilon zz already. So we can find out the three principal strain in that particular plane. Likewise, we have invariants of the strain tensor in the same way. That is, it has three invariants. J1, J2 and J3, where J1 is given by the trace of the strain tensor, or we say the trace of the strain tensor, and similarly J3 represent the third invariant, which is the determinant of the strain tensor. So invariance is same as like the stress invariants. Now the decomposition of strain tensor. Decomposition of strain tensor. So in the same way like earlier also, we break the stress tensor into two parts, hydrostatic and deviatoric part. Similarly here also we can break the stress tensor into two parts, that is the volumetric strain tensor and the strain deviator. So epsilon, which is the infinitesimal strain tensor, can be break into two parts, 1/3 J1 times identity. J1 is nothing but the first invariant of strain tensor, plus epsilon minus 1/3 J1 times identity. So this part is called as volumetric strain tensor. Volumetric strain tensor. And this part is referred as strain deviator. Next is, so this is the decomposition of strain tensor into two parts, the volumetric strain tensor and the strain deviator. We can use this, we will use this formula to find out the, to solve out the problem, which I will discuss later in this session. The next part that is discussed is the strain compatibility equation. Strain compatibility condition. So there are 6 compatibility conditions. So I just simply write here, that is del 2 epsilon zz, del 2 epsilon xx upon del y square plus del 2 epsilon yy upon del x square is equal to del 2 gamma xy upon del x del y. This is the first two equations. In the same way, we have another two equation, that is del 2 epsilon yy upon del z square plus del 2 epsilon zz upon del y square is equal to del 2 gamma yz upon del y del z. Del 2 epsilon zz upon del z square. I do one mistake here. Yeah, no, this is right. Del 2 epsilon xx upon del z square plus del 2 epsilon zz upon del x square is equal to del 2 gamma xx upon xz upon del z del x del z. And the other three equation is given by del 2 epsilon xx del by del z del gamma yz upon del x plus del gamma z x upon del y minus del gamma xy upon del z is equal to 2 times del 2 epsilon zz upon del x del y. Del by del x del gamma xy upon del z plus del gamma xz upon del y minus del gamma yz upon del x is equal to 2 times del 2 epsilon x upon del y del z. And the last equation is del by del y del gamma xy upon del z plus del gamma yz upon del x minus del gamma xz upon del y is equal to 2 times del 2 epsilon yy upon del x del z. So these are the six conditions for the strain compatibility. So this ensures the independent of the path between the two displacement line element, between the two line elements. Okay, so these are the six strain compatibility condition. So we have a special case in this one, that is the special case is the plane strain condition. So for plane strain condition, so for plane strain condition, what will happen? Epsilon xx is nothing but epsilon xx, which is a function of only x and y. Epsilon yy is only a function of x and y. Gamma xy is only a function of x and y. And epsilon zz is only a function of epsilon zz and gamma xz and gamma yz all are 0. So this is a condition for the plane strain. And if we find out the compatibility equation for this condition, that is in plane strain condition, five of the equation will be already satisfied, because you see that here in this equation that epsilon zz gamma yz epsilon zz gamma xz gamma yz gamma zx, wherever z term will come, the component of that term will be 0. So some of the equation, that is the 5 equation out of the 6 equation, is already satisfied for the plane strain condition. So the only equation that will left is the first equation, that is del 2 epsilon xx upon del y square plus del 2 epsilon yy upon del x square is equal to del 2 gamma xy upon del x del y. So we need to satisfy only this equation, and other 5 equation is automatically satisfied for the plane strain condition. So for plane strain condition, we need to only satisfy only one strain compatibility equation, which is del 2 epsilon xx upon del y square plus del 2 epsilon yy upon del x square is equal to del 2 gamma xy upon del x del y. So we need to satisfy only this equation. So this is all the brief overview of the 3 lectures. Now I will move on to the problem solving session. So let's start the problem solving session. So the above concept that I discussed in the starting of the lecture, from the starting of the lecture, will be used in solving the problem, which we will now discussing. So the first problem is problem 1. So we have to find out the strain tensor and longitudinal strain in this question. So the question is the position of a particle initially at x1, x2, x3 is defined by small x1 is given by big x1 plus k x3 small x2 is given by big X2 plus k x2. The small x3 is given by big X3, where k is equal to 10 to the power minus 5. So the first question based on this statement is find the components of the strain tensor. Find the components of strain tensor. And the next question is find the unit elongation of an element initially in the direction of E1 plus E2. So we have two questions here. So the question is the position of a particle initially at x1, x2, x3 is defined by this one. X1 is given by big X1 plus k times x3. X2 is equal to big X2 plus k times x2. X3 equal to big X3. And where k is given by 10 to the power minus 5 unit. So the first question is find the component of strain tensor, and the second question is find the unit elongation of an element initially in the direction of E1 plus E2. So here strain tensor typically means the infinitesimal strain tensor. So first we have to find the infinitesimal strain tensor solution for this question is, so epsilon is given by half of grad u plus grad u transpose, right? So first we will find out the component of grad u. So what is grad u? The first component is del u1 del x1 over del x1. So here we have to find the value of u. So what is u here? So u1 is x minus x1 minus x1, which is kx3. u2 is x2 minus x2, which is kx2, and u3 is 0. So del u1 over del x1 is 0, del u1 over del x2 is 0, del u1 over del x3 is k. Similarly, del u2 over del x1 is 0, del u2 over del x2 is k, del u2 over del x3 is 0, del u3 over del x1 is 0, 0 and 0. So this is the value of the grad u. So a component of strain tensor is given by half of grad u plus grad u transpose, which is, so this will also 0, and this will become k by 2 0. This is also 0. This will become also 0. This will become k by 2 0 0. So this is the component of strain tensor. Now the second question is find the unit elongation of an element initially in the direction of E1 plus E2. So basically we have to find out the longitudinal strain along this direction. Okay, so this is question number A. Question number B. So this question, first we have assumed that E1 prime, or we say E1 hat, is 1 by root 2 E1 plus E2. So we have to find the longitudinal strain along this direction. We basically see E. So we have to find the unit elongation along E hat direction. So strain, which is given by epsilon, is equal to epsilon tensor times E hat, epsilon E hat dot with E hat. So the component in component basic form, it can be written as 0 0 k by 2 0 k 0 k by 2 0 0 multiplied with e hat and then dotted with e hat. So it becomes 1 by root 2, 1 by root 2 is will become 1 by 2, and it is simply e1 and e2 component is here, e1 1 1 0, which is dotted with again 1 1 0. And if we calculate this, we find that it is coming out to be k by 2, and the value of k is given in the question, that is 10 to the power minus 5. So this is nothing but 10 to the power minus 5 by 2. So this is all about question number 1. So in this question we have to find two things. The first thing that is we have to find is the strain tensor, component of a strain tensor, and the second thing is to find the longitudinal strain along this direction, E1 plus E2 direction. Now move on to the next question, that is problem number 2. So in this question, the statement is consider the displacement. Consider the following displacements. Consider the following displacements, that is u1 is given as k times 2x1 square plus x1 x2, u2 is given by kx2 square, and u3 is given by 0, where the value of k is 10 to the power minus 4 unit. So we have to find the unit elongation, find the unit elongations and the change of angles for two material elements. For the two material elements, which is as dx, the first material element is given as dx1 e1 and dx2 is dx2 e2. That emanate from a particle designated by x equal to e1 plus e2. So the question is, consider the following displacements where u1 is equal to k times 2x1 square plus x1 x2, u2 is k times x2 square, and u3 is equal to 0, where k is equal to 10 to the power minus 4 unit. The question is, find the unit elongations and the change of the two angles for two material elements dx, the first material element, that is dx1 e1, and the second material element is dx2, that is dx2 e2, that emanate from a particle designated by emanate means it's coming, it's in the particle itself, designated by x equal to e1 plus e2. So here also we have to find the unit elongation, which is nothing but the uh, unit elongation in each material element and the change of angle of the two elements. So we have to find the two longitudinal strain, and we have to find also the shear strain between these two line elements. So first we have to find the value of the displacement gradient, component of displacement gradient, which is given by grad u. So del u1 over del x1. So if we take the derivative of u1 with respect to x1, we will get 4k x1 plus x2, k times x2. Del u1 over del x2, it will give us k x1. Del u1 over del x3, 0. Del u2 over del x1, 0. Del u2 over del x2, 2 times k x2, 0. Del u3 over del x1, 0, 0, 0. So we find the value of grade u. Now we find the value of the infinitesimal strain tensor, that is epsilon. So it is given by half of grade u plus grade u transpose. So this will become the same, the diagonal element will be same. Okay, so this is the strain tensor, infinitesimal strain tensor. And now it is mentioned that so the longitudinal strain along E1 direction. So unit elongation for dx1. Unit elongation for dx1 is equal to dx1 E1. So the unit elongation for dx1 is dx1 E1, and what is the value of epsilon along E1 direction? That is a strain tensor along E1 direction is 4k x1 plus k x2. And if we take the direction that is given in the question here, that is x is given by E1 and E2. So basically x component of x is 1, 1, 0. So here x1 is 1, x2 is 1, and x3 is 0. So if we find the value of this one, at x1 equal to 1, x2 equal to 1, which is 4k plus 1k, which is 5k, and the value of k is given here, that is 5, 10 to the power minus 4. So it is given by 5 into 10 to the power minus 4. The next thing that is we have to find the longitudinal strain, that is unit elongation along E2 direction. So epsilon 22 is 2k x2 at x1 equal to 1, x2 equal to 1. So it is given by 2k, which is nothing but 2 into 10 to the power minus 4. Now we also have to find the change in angle between the two line elements, which is again from this we can find out, because this is nothing but in the strain tensor it is gamma by 2, and we have to find out the value of the gamma. So angle change in angle between two line elements is gamma, and here we know the gamma by 2 value, that is kx1 by 2. So it becomes 2 times kx1 by 2 at x1 equal to 1, x2 equal to 1. So it will become k. And what is the value of k? Ten to the power minus 4 unit. So because it is in angle, so we can say this is in radian. Okay, so this is all about question number 2. Now move on to the next question, that is question number 3. So yes, problem 3. So in this question, the statement is, for the displacement field u1 is given here. u1 is equal to k x1 square, u2 is equal to k x2 x3, u3 is equal to k 2x1 x3 plus x1 square, where k is given by 10 to the power minus 6. So the question is, find the maximum. Sorry, I write the same question here. No, it's correct. The question is, find the maximum unit elongation for an element that is initially at 1, 0, 0. So this question also says we have that, but here there is a twist, that is we have to find the maximum unit elongation, that is we have to find the principal strain, maximum principal strain. So there is a two different way. We can also find use the analytically we find out the eigenvalue of the strain tensor. So we can find out the maximum unit elongation, that is the maximum principal strain. The another way is to use the Mohr circle concept. So we can also use that concept to find the maximum unit elongation. So I'm using here the eigenvalue, using to find out the eigenvalue of the strain tensor. So using that way we can find out the value of the principal strain. So first we have to find the strain tensor itself. So first we have to find the component of grade u, that is del u1 over del x1 is 2kx1, and if you calculate the value at 1, 0, 0, then it becomes 2k. Del u1 over del x2 is 0, del u1 over del x3 is 0, del u2 over del x1 is 0, del u2 over del x3 is kx2, and x2 is 0, so it also becomes 0. Del u over del x3 is kx2, that is then x2 becomes 0, so it also becomes 0. Del u3 over del x1 is k times x3 plus 2k 2x1, and x2 here is 0, x3 is 0, and only left is x1 equal to 1. So when we put x1 equal to 1, we will get 2k. Del u3 over del x2, it will be 0. Del u3 over del x3, so it will give us 2k x1, and if we put the value of x1 equal to 1, then it will give us 2k. Now strain tensor, half of grade u plus grade u transpose. So 2k 0, 0, 0, 0, 0, k 0, 2k. So this is the component of the strain tensor. Now we have to find the maximum unit elongation. So for the maximum unit elongation, we have to find the principal strain component. One simple way is to find the eigenvalue of this matrix. So we find out the eigenvalue of this matrix. 2k minus lambda, k 0, 0 minus lambda, 0, k 0, 2k minus lambda equal to 0. And we have to take the determinant of this matrix. So it will give us minus of lambda 2k minus lambda whole square minus k square. So there is a two possibility here, lambda equal to 0 or this whole expression will be 0. So 2k minus lambda equal to minus k, or 2k minus lambda equal to k. So from here we will get lambda equal to 3k, and here we will get lambda equal to k. So we find the value of the maximum unit elongation, that is lambda 1 equal to 3k, lambda 2 equal to 2k, and lambda 2 equal to k, and lambda 3 equal to 0. So the maximum unit elongation is 3k. So we can write the maximum unit elongation is 3k, and at 1 comma 0 comma 0 it is given by 3k. And what is the value of k here? 10 to the power minus 6. So it is given by 3 into 10 to the power minus 6 is the maximum unit elongation at this point, that is at 1 comma 0 comma 0. So this is question number 3. Now move on to the next problem, that is problem number 4. Problem 4. The question is, the matrix of an infinitesimal strain tensor, the matrix of an infinitesimal strain tensor as epsilon is equal to k1 x2 0 0 0 minus k2 x2 0 0 0 minus k2 x2. So we have two questions based on this statement. The first question is, find the location of the particle that does not undergo any volume change. And the next question is, what should be the relation between k1 and k2 so that no element changes its volume. So first question is, find the location of the particle that does not undergo any volume change. That is, the volumetric strain here is 0. And we know that volumetric strain is given by trace of the strain tensor. And from the question it is given as it is 0. And what is the trace of strain tensor? k1 x1 plus minus k2 x2 minus k2 x2. That will give us k1 x2 minus 2 times k2 x2, which is k1 minus 2k2 times x2. And the volume has to be 0. For volume to be 0, that is, a change in volume to be 0, this has to be 0. That is, k1 minus 2k2 must be 0. So the condition is find the location of the particle that does not undergo any volume change. So here, for to find out the location where volume change does not changes any volume, so we simply have to find whether this has to be 0 or this has to be 0. But in the first question it is mentioned that we have to find the location. So if suppose there is a location where x2 equal to 0, that means that at that location the volumetric strain is 0, because x2, if x2 will be 0, then this expression, this term will also be 0. This will become epsilon v, that is volumetric strain, also 0. So the location of the particle, if the particle is located at a point where x2 equal to 0, then at that location the volumetric strain will be also 0. The next question is, this is question number A. So this is the answer. The next question is, what should be the relation between K and K2 so that no element changes its volume? So for no element changes, suppose there is no element change, so this expression has to be 0. That is, for no element change, its volume K1 equal to 2K2. That is, K1 minus 2K2 has to be 0, which give us K1 equal to 2K2. So for no element changes its volume, we must satisfy K1 equal to 2K2. Now move on to the next question, problem number 5. So the question is, the displacement gradient matrix at a point in a body is given by H equal to del u over del x, del u over del y, 0, del v over del x, del v over del y, 0, 0, 0, 0. And the question is, write the condition for 0 infinitesimal strain. 0 infinitesimal rotation. So question, I repeat the question here. The displacement gradient matrix at a point in a body is given by this relation. The matrix is given here, displacement gradient matrix. So here you can see the third row and third column has 0 component. So the question is, write the condition for 0 infinitesimal rotation. So we have given grad u equal to h. Okay. And for 0 infinitesimal rotation tensor, the rotation tensor, local rotation tensor must have 0. So we write down the formula here. Infinitesimal rotation tensor. So this is the diagonal component is 0 here. So in the starting I write the formula for local rotation tensor. Yeah, so this is the formula for the local rotation tensor. I simply just write down there also. That is half of del u1 over del x2 minus del u2 over del x1, half of del u1 over del x3 minus del u3 over del x1, half of del u2 over del x3 minus del u3 over del x2, and this term will be antisymmetric, as I earlier told that this is a skew symmetric tensor. So as you see that there is no displacement gradient in the third row and the third column. That means there is no contribution of displacement along z direction. So we can say that all the stress component which has a contribution of stress along z direction will be 0. That means this term will be 0. This term will also be 0 because it's a derivative with respect to x3. Here u3 is there, so it will be 0. Here derivative with respect to x3, and here derivative with respect to derivative of u3 with respect to x2, so it will also be 0. The only one expression will be left here in this case, that is half of del u1 over del x2 minus del u2 over del x1 is left only, and it will be 0. So I write here all the components of the matrix are automatically 0 except which component? Except 1 comma 2 component. Okay, and for 0, for w equal to 0, half of del u1 over del x2 minus del u2 over del x1 equal to 0. Must be 0 because all the individual component must have 0 component, because it says in the question that w has to be 0. And from this we can say that del u1 over del x2 equal to del u2 over del x1. So this is the condition for zero infinitesimal rotation tensor. So the question is asking about the condition. Write down the condition for zero infinitesimal rotation tensor. So yeah, we write the condition here, that is del u2 over del x1. Now move on to the next question, that is problem number 6. So the problem is, given the following formula, for strain components. For strain components, and the formula given here is epsilon xx, that is longitudinal stress along x direction, is given by 5 plus x square plus y square plus x to the power 4 plus y to the power 4. Epsilon yy is given here as 6 plus 3x square plus 3y square plus x to the power 4 plus y to the power 4. Epsilon gamma xy is given as 10 plus 4xy x square plus y square plus 2, and epsilon zz, gamma yz, and gamma xx all are 0. So based on this statement we have two questions. That is, the first question is, determine whether the above strain field the above strain field is possible. If it is possible, if it's possible, determine the displacement components in terms of x and y. Assume that ux equal to uy is equal to 0 and wxy equal to 0 at the origin. And the second part of this question is, for the state of strain given in previous problem, write down the spherical or you say volumetric, write on the volumetric and deviatoric parts. And also determine the volumetric strain. Okay. So here the question is, for the state of a strain given in previous problem, write down the volumetric. So I am repeating from the above, that is problem number 6. Given the following formula for the strain component. So this is the formula for the strain component: epsilon xx, epsilon yy, gamma xy are given in terms of x, y, and z. The question is, and epsilon zz, gamma yz, gamma xx, sorry, gamma xy is here, gamma zx is here, gamma x zx, gamma zx is 0. And the question is, determine whether the above strain field is possible or not. If it's possible, determine the displacement component in terms of x and y. Assume that ux is equal to uy equal to 0 and wxy is equal to 0 at the origin. The second part of this question is, for the state of a strain given in the previous problem, write down the volumetric and deviatoric parts and also determine the volumetric strain. Okay, so yeah, let's begin with the solution. So first you can see from the question here that epsilon zz, gamma yz, and gamma zx equal to 0. That means we can say that it's a condition of plane strain condition. And for the plane strain condition, we have to satisfy only one compatibility relation. The question is, determine whether the above strain field is possible or not. So for the strain field, if the strain field is possible, then it must have satisfied the strain compatibility conditions. And for the plane strain condition, we have to satisfy only one component of strain compatibility equation, that is the first equation. So I write down here, the above strain field represents a plane strain condition. Okay. So only 1 out of 6 strain compatibility condition needs to be checked. Other five are trivially satisfied. That is, we have to satisfy only one equation, that is del 2 epsilon xx upon del y square plus del 2 epsilon yy upon del x square equal to del 2 gamma xy upon del x del y. Okay. So the first equation is del 2 epsilon xx upon del y square plus del 2 epsilon yy upon del x square equal to del 2 gamma xy upon del x del y. So starting from the LHS, we have to satisfy LHS equal to LHS for the given question. So del 2 epsilon xx upon del y square plus del 2 epsilon yy upon del x square is given by epsilon xx upon so we have to take epsilon xx derivative, second derivative with respect to y. So it will only left 2y and then 2. So 2 plus 4x 4y cube then 12y square. 2 plus 2 12y square. 2 plus 12y square. Then del 2 epsilon yy upon del x square. So we have to take this one with second derivative with respect to x. So this will give us 6 and this will give us 4th x cube, then again derivative with respect to x will give us 12 s x square. So it will give us 6 plus 12 x square, and we compute this 12 x square plus 12 y square plus 8. Okay. Now this is the LHS. Now coming to the RHS part, that is del 2 gamma xy upon del x del y. So first we have to take derivative with respect to x and then with respect to y. So if we take the derivative with respect to x, then it will give us 4 to x square x cube. So here 12 x square y plus 4xy then 4y cube, 12x square y then 4x cube, sorry 4y cube, and then with respect to y will give us 12y square. So it will give us, first with respect to x will give 4x cube, that means 12x square y plus 4y cube plus 4y cube plus 4y, that means 8y. And if we take the derivative with respect to y, it will give us 12x square plus 12y square plus 8. And we see from these two that it is same. So we can say equation 1 and equation 2 is satisfied, as equation 1 and 2 are equal, strain field are possible. So this is the first part, and the question says, if it is possible, determine also the displacement component in terms of x and y. So we know the displacement component, we know the strain in terms of displacement, that is epsilon xx is given by del ux over del x, which give us ux equal to integral over epsilon xx dx. And if we take the integration of epsilon xx with respect to dx, then it will give us 5x plus x cube by 3 plus y square x plus x to the power 5 by 5 plus xy to the power 4 plus f function of y. Similarly, epsilon yy is given by del uy over del y, which give us uy is equal to integral over epsilon yy with respect to dy. So it will give us 6y So if you see the epsilon yy relation, that is 6 plus 3x square 3y square x to the power 4 y to the power 4. Then if we take the derivative, if we integrate it with respect to dy, then it will give us 6y plus 3x square y plus 3y cube by 3 x to the power 4y y to the power 5 by 5 plus g of x. So 6y plus 3x square y plus y cube plus x to the power 4 x to the power 4 y plus y to the power 5 by 5 plus gx. Now we have to find the value of fx, fy and gx. And here you see that fy and gx are not a function of z because we are dealing with only plane strain condition and there is no strain along z direction. So we can say it's only a function of y, and if we take the if we integrate it with respect to y, then it will give a function of gx, and if we integrate epsilon xx with respect to x, it will give a function of y. Moreover, we also have one more equation, that is gamma xy. Gamma xy is given by del ux over del y plus del uy over del x. That means we have to take the derivative of ux with respect to del y and derivative of uy with respect to x, and from here we can take it. So derivative of ux with respect to y will give us 2xy plus 4xy cube plus f derivative of fy with respect to y, that is f prime y plus 6xy plus 4x cube y plus derivative of g with respect to x, that is g prime x. So this is the value of gamma xy. Now here from the question, if we compare this equation with this equation, then we found some relation, that is gamma xy is from the question is, I just copy it from here. So from the question, gamma xy is given by this relation. Okay, so if we compare this one, this equation with this equation, we found that f prime y plus g prime y, f prime y plus g prime x equal to 10. That is, if we compare this one, these two, then we can get from there that f prime y plus g prime x equal to 10, which give us f prime y equal to 10 minus g prime x. Okay, and f prime y plus g prime x will give us a constant value. Okay, that means the LHS is a function of y and RHS is a function of x, which can be true only when they are both constant, which means that f dash y equal to 10 minus gx, both are a constant value, which is some say d. So this 2 must be a constant value. So from here, this 2, we can find that fy equal to c1y plus c2. If we take integration of this one, then we can find the fy equal to c1y plus c2. And if we take the integration of this one, gx, then it will give us gx equal to 10 minus d x plus c3, some constant c3. Now here we find the fy and gx in terms of x and y, but the question here is we have to find the constants here. That is, we have 4 constants here: c1, c2, d and c3. We have to find this one, and for this we have given the boundary condition. So we are using that displacement boundary condition first. So the question boundary condition is given here, that is, assume that ux uy equal to 0 and wxy equal to 0 at the origin. So the displacement boundary condition is being prescribed here, so we will use that boundary condition here. Using the displacement boundary condition at origin, so ux at origin, that is 0, 0 equal to 0. That means f of 0 equal to 0. That means c2 equal to 0 from this equation. From this equation we can find out this one. Now uy at origin equal to 0, which means g at 0 equal to 0, which means c3 equal to 0. Okay, now the last boundary condition that is being prescribed here, wxy at origin equal to 0, which means half of del ux over del y minus del uy over del x at origin equal to 0. And what is del ux over del y and del uy over del x? So del ux over del ux over del y at x equal to 0 and y equal to 0. So this only will left here, that is f prime y f prime y and minus del uy over del x. So del uy over del x is here, that is gx. So g prime x at origin equal to 0. That is f at 0 minus g prime at 0 equal to 0. And what is f at prime 0 minus g prime 0? So if we see from here, yeah, g prime x, so it gives us 10 minus d. And what is f prime 0? So f prime is give us 10. Sorry, d. It's d. Yes. F prime y is d. So it gives us d and it gives us 10 minus d. So from here d equal to 5. Now what is f? Coming to the fy relation. So what is f prime y is d. F prime y is d and d equal to 5. So what is fy? Fy is 5y. Similarly, what is d prime y? D prime x? D prime x is g prime x is 10 minus d. 10 minus d. And what is d? 5. So it's basically 5. And g prime x is gx is then 5y, 5x. So this is the expression of fy and gx. So therefore the final displacement component, therefore the displacement component are, so from here we can say the displacement component. So from this, sorry, from here ux, uy and gamma xy, we can know the expression of this one. So ux is given by 5x plus x cube by 3 plus y square x plus x to the power 5 by 5 plus x to the power xy to the power 4 plus 5y, because here it is fy. Uy is given by 6y plus 3x square y plus y cube plus x to the 4y, x to the power 4 into y plus y to the power 5 by 5 plus 5x, and gamma xy is given by, so here only we have to find the displacement component. So we found that expression of displacement along x direction and displacement along y direction. Okay, so this is all about the first part of the question. Determine whether the strain field is possible. So yes, it is possible, and if it's possible, determine the displacement component in terms of x and y. So we already found that the displacement component ux and uy. The next part of this question is, for the state of a strain given in the previous problem, write down the volumetric and deviatory part and also determine the volumetric strain. So yes, question number B, solution. So volumetric strain tensor is equal to 1 by 3. J1 is the first invariant of the strain tensor times identity. And what is J1? First we have to find the J1, which is epsilon xx plus epsilon yy plus epsilon zz, which gives us 5 plus x square plus y square plus x to the power 4 plus y to the power 4 plus 6 plus 3x square plus 3y square plus x to the power 4 plus y to the power 4 plus 0, because epsilon z here is 0. It's a plane strain condition. So if we simplify this, we will get for 11 plus 4x square plus 4y square plus 2x to the power 4 plus 2y to the power 4. So this is the value of first invariant of the strain tensor. Now volumetric strain tensor. So from here 1 by 3 J1 into identity. So volumetric stress tensor is given by 1 by 3 Jacobian. What is Jacobian? First invariant of the strain tensor is 11 plus 4x square plus 4y square plus 2x to the power 4 plus 2y to the power 4 times identity. And deviatoric strain tensor is total strain tensor minus volumetric strain tensor, which is 1 by 3 11 plus 4x square plus 4y square plus 2x to the power 4 plus 2y to the power 4 times identity. Okay, so this is the volumetric and deviatoric strain tensor. Is there anything else in the question? Yeah, so we found out the volumetric and deviatoric strain. So this is only this question is here. Sorry, one more question is here. And also there is a last question, that is we have to find the volumetric strain. So volumetric strain, that is epsilon v. So epsilon v is given by trace of strain tensor, that is epsilon xx plus epsilon yy plus epsilon zz. And here in the question epsilon zz is 0, there is only epsilon xx and epsilon yy. So if we add the two things, we will get epsilon xx is given by 5 plus x square plus y square plus x to the power 4 plus y to the power 4, and epsilon yy is 6 plus 3x square plus 3y square plus x to the power 4 plus y to the power 4, and it will give us 11 plus 4x square plus 4y square plus 2x to the power 4 plus 2y to the power 4. So this is the final answer of the volumetric strain. Okay, so this is all about question number 6. Now move on to the next question, that is question number 8. So this, now the question is, the upcoming question is based on the theoretical part. So yeah, question number, problem number, this is problem number 6. So the problem number 7 is, which of the following strain, so this is a multiple choice question, which of the following strains is independent of line elements chosen at a point? The option is longitudinal strain, shear strain, volumetric strain, and none of these. Which of the following strain is independent of the line element chosen at a point? So the longitudinal strain is based on the direction of the line element, so it is not correct option. Shear strain is also based on the direction of the line element, but the volumetric strain is independent of the line element chosen, so it is the correct option, because it depends totally on the summation of the longitudinal and strains in all the three directions. so it is independent of the line element. So the correct option is volumetric strain. The next question, that is problem number 8. So this is also a multiple choice question. Which of the following formula represents the volumetric strains? And the options are: volumetric strain is given by det of f, determinant of f minus 1. The second option is volumetric strain is given by del u 1 over del x1 plus del u 2 over del x2 plus del u 3 over del x3. The third option is volumetric strain is given by trace of grade of u. And the fourth option is volumetric strain is given by half of trace of grade u plus grade u transpose. So if you are in the meeting from the starting, then you obviously do this question very easily, because in the starting of the session I have briefly give the overview of the lectures. So yeah, the first option is volumetric strain is given by determinant of f minus 1. So yeah, it is correct option because it is given by det of f, that means deformation gradient tensor, determinant of deformation gradient tensor minus of 1. The second option is volumetric strain is given by the del u over del x1 plus del u 2 over del x2 plus del u 3 over del x3, which is also correct option because volumetric strain is given by trace of the strain tensor, and here it represents the trace of the strain tensor because you see the summation of all the diagonal elements. So yes, it is also a correct option. The third option is volumetric strain is given by trace of the gradient of u, that means the displacement gradient, the trace of displacement gradient tensor. So yes, this is also true because the trace of displacement gradient will also give the summation of all the longitudinal strain. The fourth option is the volumetric strain is given by half of the trace of displacement gradient plus transpose of displacement gradient. So yeah, this is also correct because this is nothing but the half of grade u plus grade u transpose is the strain tensor, and if we take the trace of it becomes the longitudinal volumetric strain. So here all options are correct. So the question is, which of the following option represent the volumetric strain? So yes, all of the 4 options represent the volumetric strain. Now coming to the next question, that is problem number 9. Why volumetric strain is local in nature? And the options are: the first option is because change in volume per unit volume is different for different parts of the body. The second option is because change in volume per unit volume is same for different parts in the body. The third option is local is just a name. Local is just a name given to volumetric strain. Local is just a name given to volumetric strain. It doesn't signify anything. It doesn't signify anything. And the fourth option is none of these. So the question is why volumetric strain is local in nature. So the first option is why we say volumetric strain is local in nature, because change in volume per unit volume is different for different parts of the body. So yes, it's correct option, because at every part of the body there is a different volume change per unit volume. So this is a correct option for the given question. Now move on to the next option, because change in volume per unit volume is same for different parts in the body. No, this is not a correct option, because at different part of the body the change in volume per unit volume is different, not the same one. And the third option is local is just a name given to volumetric strain. Yeah, here it is a strain. Yeah, so the third option is local is just a name given to volumetric strain. It doesn't signify anything. No, this is not correct. Local is not just a name, because whenever we say volumetric strain, it is local in nature. That means at every part of the body, at every point in the body, there is a different volumetric strain. And the fourth option is none of this. So the only correct option is option number A. So here only for one option is correct, that is option number A. Now we have another question, and this is the last question for the session today. That is problem number 10. The lateral strain is option A, the ratio of axial deformation to the original length. The next option is the ratio of the ratio of deformation in area to the original area. And the third option is the longitudinal strain in a line element oriented at right angle to the direction of applied load. And the fourth option is the ratio of length of the body to the tensile force applied. On it. So here the question is the lateral strain is basically the definition of lateral strain has been asked. So the options are the ratio of axial deformation to the original length. So no, this is not the correct option, because it is not about the lateral strain, the ratio of axial deformation to the original length. This is not the lateral strain actually. So this is the wrong option. The next option is the ratio of deformation in area to the original area. This is also not correct option because there is no strain on the basis of area. The third option is the longitudinal strain in a line element oriented at right angle to the direction of applied load. So yes, this is a correct option because it is saying that the longitudinal strain in a line element oriented at right angle to the direction of the applied load. So if we apply the load along x direction and there is a strain in the y direction, that means it is perpendicular to the applied load. But we are talking about only the longitudinal strain. Then we say that if there is a load in the x direction and if there is a possible there will be a strain in the y direction, then we say that will be a lateral strain in the y direction. So yeah, this is the correct definition of the lateral strain. The fourth option is the ratio of length of the body to the tensile force applied on the it. No, this is basically a very incorrect option because here the length and the force are being compared. So yeah, this is absolutely wrong option. You can also say that this can't be possible anymore because anyway it can't be possible because the length has different unit and the force has different unit, but we know that strain has no unit. So yeah, this is the wrong option, of course. So the correct option here is option number C. So this is all about today's session. So today we have solved 10 questions. So uh, I hope you understand it. And if you have any doubt, please ask in the chat box in the YouTube channel or in the next session. In the coming Friday, I will take the next session based on week 6. So yeah, thank you for joining today. You can leave the meeting now.